So I've kind of looked ahead at this chapter 4 stuff that's on Schoology, and from what I can tell, I was not sure if the next thing you guys would be doing would be applications or graphing, and it looks like what you're doing is a combination of both, and they do kind of go together. So the whole idea is that with calculus, you can apply it to a lot of real-world situations, specifically finding critical values of functions because that has meaning in the real world. Like, what is the maximum profit that can be generated by selling a certain product? Or how can we minimize the cost of production of a product? Or, what's the biggest house I can build on the top of this cliff and have it not, collapse in a landslide when it rains? So those are actually all real world situations that can be described with math and using calculus to find minimums and maximums. So that's kind of where we're going with all this. Problem number 1 on the worksheet asks you to find the absolute maximum and minimum values of a function on a given interval. So the absolute maximums and minimums will happen in only several of places. They can happen at the endpoints, so at the ends of the interval, or they can happen at any critical values of the function. So for that, we're looking for maximums where the derivative is equal to 0, places where the derivative is undefined. So those are the other critical values where a maximum and minimum might occur. So I took the derivative of my function, and I got -6 over x minus 4 squared. I did the whole low d high minus high d low thing. And there is no place that is equal to 0. So I have no local maximum or minimum for the function. There's no place where the derivative is equal to 0. That means that the only critical points are going to happen when x is equal to -1 or when x is equal to 3. So the only thing I have left to do is to plug in -1 into the function, and I get -1/5. I plug in 3 to the function, I get -5. So that means that my maximum must be -1/5, and my minimum must be -5. And I neglected to mention this before, but what I'm doing on this worksheet is making problems just like the problems on the worksheet, so that you can see what I'm doing, but then go ahead and do your own work when you're doing the problems. So on to problem number 2, which asks us to find any critical points and any extreme values of a function. So I put together a different polynomial, not sure how it's going to work out yet, but the idea is going to be the same. We're going to take the derivative of it, we're going to set the derivative equal to 0, and those are going to be our maximums and minimums, and then we're going to take those x values, plug them back into the original function, and find out the value of the maximums and minimums and any critical points. So when I set the derivative equal to 0 and solve the resulting equation, I get x is equal to 0 and x is equal to plus and minus root 3. But I still don't know what the minimums and maximums and extreme values are, because now what I have to do is plug these x values into the original function and find out what my outputs are. So now plugging into my original function, when I plug in 0, I get 0. When I plug in root 3 into the function, I end up getting, well, you see me doing all this stuff here, but I end up getting approximately -4.16. And when I plug in negative root 3, I end up getting positive 4.16. And so my critical values, or my critical points, are 0, 0, root 3, and this negative 12 root 3 over 5 is my minimum, and negative root 3 at 12 root 3 over 5 ends up being my maximum. All right, so the third problem on that first page is to find the critical points of a trig function over the interval 0 to 2 pi. So I tried messing around with some different ones, and it was hard to find one that would cooperate. So finally I found one. So I've just got sine x plus cos x. And again, we'll take the derivative. We'll set the derivative equal to 0, and we'll find those critical points. So the derivative in this case is pretty easy. The derivative of sine x is just cosine of x. And the derivative of cosine x is negative sine x. So when I set the derivative equal to 0, I can add the sine to the other side. So cosine is equal to sine. The two places where that happens on the unit circle are in the first quadrant and in the third quadrant. In the first quadrant where they're both positive at pi over 4. In the third quadrant where they're both negative at 5 pi over 4. And so that gives me the x values of the critical points, the y values of the critical points at pi over 4. We get root 2 over 2 for sine and root 2 over 2 for cosine. Altogether, that's just root 2. And at 5 pi over 4, sine and cosine are both negative, so it's negative root 2 over 2 plus negative root 2 over 2. So then we have a maximum value at pi over 4 root 2 and a minimum value at 5 pi over 4 negative root 2. And those are the critical points for the function sine x plus cos x from 0 to 2 pi. But we've got to be careful because we do have a defined interval. So we have to plug in those endpoints to get critical values as well. In this case, I almost forgot to do that simply because I knew that when I plugged in 0, when I plugged in 2 pi, I would not be getting these maximums or minimums. Root 2 and negative root 2 are outside of that. But when I plug in 0, I get sine of 0 is 0, cosine of 0 is 1, so I get 1. And 2 pi is coterminal, so we also get 1. So 0, 1, and 2 pi 1 are also important critical points for the function sine x plus cosine x on the interval 0 to 2 pi. But the other ones that we found before are the minimum and the maximum. So that's it for page 1. Again, just a quick recap. To find the critical values and maximums and minimums, we're looking for the endpoints on the interval. We are looking for places where the derivative is equal to 0 for possible minimums and maximums, or local minimums and maximums, and also possibly, although we haven't run into any yet, places where the derivative is undefined or the function is undefined, because they may be critical points or extreme values as well.